Hello, and welcome to another Rocky Mountain Smiths online demonstration. My name is Evan Blackstock. I'm streaming from my garage in Arvada, Colorado. Today we're going to be talking about induction heating or induction forges as used by blacksmiths. So first of all, what is induction heating and how does it work?
Induction heating occurs when a conductive material is exposed to high-frequency alternating magnetic fields. This induces a current in the material in the form of low-voltage, high-amperage eddy currents, which heat up the material due to the resistance of the current moving through it. This is commonly called the Joule heating effect. These eddy currents tend to form perpendicular to the length of the coil, hence the very localized heat through the cross-section of the material. Before we begin, I want to offer a big thanks and shout out to Eric Jurgensen. His YouTube channel, Edge of the Anvil, has a variety of videos on induction heating, and a lot of the information from this video I learned from him and his excellent videos online. Be sure to check out his channel for more induction forging projects.
So this is the machine that I purchased. This is the HT15KW. And as far as I can tell, it's sort of a generic version of the more popular SP15A units that you can also find. This machine, of course, they're all made in China, but I bought this one on eBay and it actually shipped from LA area and arrived in maybe 5-6 days in a nice little crate. The cost of this machine was a little over $500. And I thought at that price point it might be worth sort of experimenting with this. As a hobbyist smith working in my garage, I wanted something where I could do quick heats for one-offs and have something that's not producing a large volume of heat or fumes for my workspace. Once you've purchased the machine, there's a decent amount of work to do to set it up. You're going to need a cart for it, a cooling system, and provide electrical for it.
Looking through the manual, it didn't say how many amps this machine draws when being used. So I had to do some tests, but figured out it draws up to close to 30 amps at full power. So this cord and plug are rated for 30 amps and it's on a 30 amp breaker. Wiring it up is pretty simple. It's just got the 2 hots and a ground. And in this case, the cooler is also hooked in because it is 220 as well. In order to function properly, the machine needs a coolant system to run. You'll notice in the back there's 2 water ins and 3 water out lines, which circulate water through the internal components of the machine, as well as the copper coils to keep them from overheating. The type of cooler you use is very important for these machines. They need to have a high flow rate. This machine is 6 liters a minute required, and also a high pressure in order to pump water through the coils, especially if you're using 1/4-inch tubing for the coils. This is an older Bernard TIG welding cooler that I got for cheap on Craigslist. You can find videos of people using all kinds of wacky stuff online, but I think you really need a rotary vane type pump in order to have the pressure and capacity for these machines. Shortly after purchasing this cooler and getting it cleaned up, I realized that the pump was really worn out and had to replace it. Once I replaced the pump, it was working for a little bit and then the motor seized up. A good lesson in buying older equipment. So I ended up having to replace the motor and the pump for this cooler unit, and now it runs great. When you're looking for a pump, try to find a Procon pump if you can with a filter on the side. So this little unit here is a mesh filter, which I think is necessary for this process because if you get contaminants in the line, you want them to be strained out as it's pumping through there. Whether you're using a TIG cooler or you're making your own system, the setup is pretty simple. You have an intake here from your water reservoir that goes through a little radiator with a fan blowing on it, in this case one that's hooked up to the motor. And then this is the output here, which goes up to the machine. That hits a Y for the 2 inputs for the machine, and then the 3 outputs come down here, here, and here, And you can see I've just drilled some holes, and there was one existing hole where that just dumps back into the reservoir in the bottom.
One thing to note is if you don't have sufficient water pressure, when you turn the machine on, you'll get a water lack air light.
Once you've figured out the power and cooling requirements and have it all hooked up, you'll need some kind of cart to put the machine on. I've made this one out of scratch so that I can make it just the right size, so it doesn't take up any more space than necessary, and I can wheel it around. The top of the cart is just 16 gauge steel, and then I cut a kiln shelf that fits on the shelf. Although the coil is high enough that it shouldn't heat the metal surface below it, I generally think it's a good idea to have fire brick or a kiln shelf or something non-conductive underneath the work area for safety reasons.
First off, you want to turn on your ventilation and make sure the water pump is running on your machine. When the machine is in manual mode, you simply press on the pedal to start and stop the heating process. With the pedal depressed, you'll see a time display showing the number of seconds elapsed during the heating. You'll also see the output current in amps, which can actually be adjusted for different temperatures or intensities of heat. To heat the material in manual mode, simply depress the pedal and insert the material into the helical coil. You'll notice that when the machine is running, it emits a beeping noise. This is a safety feature so that you know it is on or currently running, since there are no visual indications that it is. You'll notice how fast the heating process is and how local it is. You can hold your fingers very close to the heat. And in addition, the coil is still cool to the touch. In automatic mode, you can set time for the heating time, the retaining time, and a cooling time that the machine will run for before automatically shutting off. The heating time corresponds to the heating adjustment knob. Retaining time refers to the retain power adjust knob, so you can have a different setting for this. This is typically used for heat treating or if you want a part to soak at a certain level. To start the process, you press the start button and you'll notice which section it's on. Right now it's heating, which it'll do for 10 seconds. Now it's on the retain mode, which is at a reduced amperage of 445, and finally the cool down of 5 seconds. Here's an example of the machine working in automatic mode. Although not as used as the manual mode, it does have its benefits in that you can find the perfect heat for heat treating or doing a batch heat of the same object, and then repeat that heat consistently over and over again. Generally speaking, you want the coils to be as close to your material as possible for the most efficient heating. You'll notice here that this 1/4 inch piece of rod will only heat to orange heat, although it looks brighter on the camera, because the coil size is too big for this material. However, if I put a 1/2 inch bar in the same coil, you'll notice that it heats much more efficiently and will get up to a much brighter heat than the 1/4 inch rod can. You'll notice that when the material is paired with the correct size coil, the heating is very efficient. This 1/2 inch rod will get up to a welding temperature in just about 30 seconds.
If the material is too big for the coil being used, you'll notice that when you start to heat it, the amperage will drop down to 0 and the machine will make a clicking noise instead of starting. This is because the inductance is too high. However, if you slowly insert the material while the machine is running, you'll notice that it'll heat the end of the material and then eventually the whole area inside of the coil. This is because as the material heats up, its inductance decreases and the machine can stay in range. Another way to solve this would be to use a coil with fewer loops, or to use a larger size coil for this material. Changing coils on the machine is fast and easy, so it is good to be in the habit of changing coils that are best suited for the material being used. Although the magnetic fields are strongest inside of the coil, you can use different parts of the coil to heat materials. Here we are heating a bent corner using the outside end of the coil rather than the inside of it. Although slower, you can still heat a variety of different shaped objects this way. One way to visualize these magnetic fields, or the heating pattern produced by them, is to use a piece of sheet metal and heat it near the coil.
One of the tricky things about making coils for these machines is that they're designed to use 8mm copper tubing. So the flare fittings are all designed for 8mm copper tubing, which is incredibly hard to find in the US. Most copper tubing in the US is 1/4 inch or 5/16, which is just a hair smaller than 8mm. Although you can find 8mm copper tubing on eBay, that's where I got this spool here, the bigger material is harder to bend, especially for tight turns on coils. To get around this, most people buy 1/4 inch tubing, which is readily available at big box stores, and then solder on a length of 8mm tubing onto the ends where it connects onto the machine.
Another challenge is finding the flare nuts required to attach the coils to the machine. These 8mm by M14 flare nuts are even harder to find than the 8mm copper tubing. Fortunately, I have found them at Metalworks for a reasonable price and they ship incredibly fast.
One question you might have is, so does the 8mm tubing with the larger diameter and mass have a better effect on inductance and heating time? And the answer is no. Basically, these two coils are exactly the same. One's a little rougher, but this is 8mm and this is 1/4 inch tubing. And doing tests, the 1/4 inch is the same, if not slightly better than the 8mm version of it. In the machine's manual, it specifies that the coil length should be 200 to 600 millimeters in length. So when I'm making a coil, I typically start by cutting about a 24-inch long piece of 1/4 inch tubing, which is about 600 millimeters, bend the coil around a pipe or a piece of wood or even a 3D printed die, then trim the ends down and replace them with the 8mm leads on the bottom to connect to the machine. Although it depends on what you're doing and the desired results, I've found a good rule of thumb is typically 3 to 5 turns on a coil, and with smaller diameters you can get away with up to 5 turns, and as you get larger you have to typically drop down to about 3 turns.
Here are some tools that I've found quite handy for working with the copper tubing. For cutting it down, I typically use a portaband on a stand, or a bandsaw would work, but even a hacksaw is a quick way to cut through it. Otherwise, you can use pipe cutters. If there's room, you can use a full-size pipe cutter. If you don't have room, these compact ones work really well for doing the final trimming of the ends of the tube. because it can rotate around and not hit the other side, so you don't have to bend out the side to cut it. And of course the pipe cutters make a pretty clean, nice cut. Once you cut it, I found a reamer and a countersink very handy for cleaning them up. So the reamer tends to get a little bit deeper in there and clean out the inside, and then the countersink on a drill or even by hand, it's good for just cleaning up that end. I also found this little tool, and this goes in a drill, and it's for deburring the outside of the tubing. And actually I found just using this by hand, giving it a few turns, works really well at kind of cleaning up that outside edge if it's got a burr on there. Another handy tool is this tubing expander. Basically, when you squeeze this, it expands, and it's used for expanding the ends of tubes so they fit together. This can be really handy if you're going to make an 8mm lead that your coil is then soldered into, because by itself, often it doesn't quite fit in there. It needs to be just a tiny bit bigger. Sometimes you can force a little bit. But once you give it a few squeezes with this guy, then it's enough to fit in there, no problem, so you can solder it like so. Some other tools, you'll need a flaring tool like this one to create the flared ends where the flare nuts attach to. Probably one of the most used tools I have is this tubing bender. You can see this one will actually go all the way to 180 degrees. And it's got 1/4 inch and 5/16, so the 5/16 works for 8mm, which is pretty handy. Whenever possible, I try to use this tool because it just makes really nice clean bends in the material, but obviously it's kind of limited in what you can do with it. Sometimes I have found that I can clamp this in the vise and actually just use these dies and press the tube against it, which is another way of using it that I found quite handy. Another really handy tool for bending are these sort of bending pliers that I found. I got this on Amazon. I think they were 20 or 30 bucks, and this has been one of the more handy tools for adjusting. It had another die up here for 3/16, but I cut it off with a cutoff disc on the grinder just so I had more clearance, and I could kind of get this into smaller spaces. But basically the way this works is you clamp it in here and then you pull it towards the direction you want to bend, and it's really handy for making tighter bends and little adjustments. Some other tools that are good for adjusting coils. I took a screwdriver and I kind of ground off the sharp edges around here, and if you take a flat screwdriver, you can put into coils and give them a twist, and it's real good for just kind of expanding coils and moving them around a little bit. If you need a little more movement, this is a simple tool I made just for expanding it a little bit further. So this will open it up just a little bit more than the width of that screwdriver. Oops. Another tool I found really handy is this little vise. This little vise was actually for filing nuts in the string instrument class that we have in the wood shop. And Bill got a bunch of these little vices so students could hold the bone nuts for string instruments and file them, but he found that they didn't actually work very well, and they haven't really used them very much. So there's a bunch of these around. But what they're really handy for is they can grab parts of these coils and kind of reopen crushed parts of the tubing. You can also close it and then open it to expand or sort of compress the coils. So this has actually been a really handy little tool. I'll put this in the leg vise, and then it's nice and secure, and I can just open and close it in the bigger vise. Another really handy tool, obviously, is just a small dead blow mallet. This size I feel like is perfect for just straightening out a coil. You can lay it on the anvil and just give it some light taps, and that'll straighten out the tubing or straighten out a curve a little bit if something's curved a little bit too much. And so that works great. And then the post vise itself, or a different vise with wider jaws, is also an excellent tool for just straightening tubing. Put it in there and just with real light pressure, clamp it down a few times while rotating it, and that will actually straighten out tubing quite effectively as well. If you know you're going to be making some tight bends, I've found it helpful to anneal the copper pipe before working with it. I've also found it helpful to seal the ends by folding them over, and then filling the portion of tube with water. This helps to keep the sides from collapsing when you're doing tight bends in the material. If you have a water pick at home, it works well for filling up these tubes. Often simply bending over a section of pipe is one of the easiest ways of making a coil. This is a rather large pipe because I wanted to try making a large coil out of 8mm tubing for some larger stock. You can see that at this size, even the 8mm tubing bends quite easily. And typically once you're done, because the material springs back a little bit, you can easily slide it off of the pipe. You can also use a variety of shapes of wood to bend the copper tubing around as a mandrel. Depending on the shape that you're working with, you may have to make the center of the mandrel removable so that you can extract it out from the center of the coil. If you don't do this, sometimes it gets stuck in the coil and can be difficult to remove without expanding the coil or burning it out. Another option is using 3D printed bending jigs. The advantage of this process is that you can incorporate the die shape for the tubing into the design and get perfect spacing for the coil that you have in mind. This little coil was a bit of an experiment to see how small I could go without having the sides of the tubing collapse. Even though the inner diameter is only a little over ½ an inch, I was still able to make a small usable coil from this. And overall, I think this technique has a lot of promise. Often some adjustments are necessary after bending the coil. Once you've made your coil, you'll need to flare the ends or the 8mm leads so you can attach it to the machine. Flaring tools like this are readily available from hardware stores for pretty cheap. However, I have found they are not worth it. Instead, it is better to get an eccentric cone type flare tool. This type of tool does a much better job at flaring the ends, and you have to fuss with it a lot less. When you're setting up the tool, I've found that about 1/16 of an inch sticking up is a good distance for getting the correct flare. It's important to get good clean flares on the ends of your coils, otherwise where it attaches to the machine you can get a slow leak or drip. Once the ends have been flared, you can go ahead and solder the 8mm leads onto your coil. Don't forget to put the flare nuts on, and then I usually use a small torch to do the soldering. Although you can use the induction heater, I find this to be quick and easy. Helical coils are the most common type of coil for this process, and whenever possible you should use them because they're the most efficient at heating stock. You can make them in a variety of shapes and sizes to suit your needs. Let's take a look at some of these coils in use. Rectangular coils are especially useful, not only for flat bar, but for a wide variety of materials and shapes. Because of their length, you can often fit in curved pieces, or those with details on the end, like a leaf or scrolls even.
This coil is what I call a variable diameter coil. It was a bit of an experiment, but the idea is that it could accommodate a different variety of sizes all within one coil rather than having to swap it out. So larger stock you would use on this side of the coil, and then working with smaller stock you'd use over here on the smaller end of the coil. This helps heat the smaller stock more effectively rather than being in a larger coil. I've also found it to be quite handy for other shapes, and if you're doing a taper, you can hold it at an angle and rotate it very carefully to get a heat that way. It also works well for heating up a variety of flat bar sizes, and if the heat is uneven, you simply take it out and rotate it and put it back in at some point during the heat. This is my attempt at making an open or a C-shaped coil. These coils are handy for stock sizes or shapes that won't easily fit inside of a helical coil. Although this works, I'm not super happy with it and plan to remake it, this time with a slightly longer length. Eric Jurgensen made sort of a version of this that he jokingly calls the taco coil, and it looks to be quite effective even getting up to welding heats. Okay, next up we have the pancake coil, which, let's see, where is the pancake coil? Oh. Thanks, buddy. The pancake coil is another open coil design that is especially useful for flat materials like flat bar or sheet goods, or really anything that won't easily fit inside of a helical coil. Some of the disadvantages of a pancake coil is that the heating can be sort of uneven or hard to predict, and sometimes it doesn't have a lot of depth, so it's hard to get the full penetration of heat through your material with thicker materials. That being said, it's a very versatile coil and one that I've actually found quite useful.
You can see that with cylindrical stock, it takes quite a bit longer to heat the material up than with the helical coils. That being said, within a minute or so, it is up to a nice bright forging temperature, and I have gotten up to welding heats with this pancake coil. As you can see here, it is much better suited for flatter stock. The material heats up quicker, and you can kind of choose where you want the heat, similar to working with a torch. Here I am preparing 1/2 of these small handy tongs to dish the palm and get ready to bend the fingers.
One thing you can do is put different diameter turns on the same coil. This wacky thing was sort of an experiment to basically make a coil that would produce very narrow heats in several different stock sizes. I found it quite useful for making bends when you just want a narrow heat in one cross section of the material.
As you can see, with only 2 turns in the center coil, it takes considerably longer to heat up the cross section of material. However, given another minute or 2, it can easily get up to a nice forging heat.
These 2 pieces of 3/8 inch square bar have been bent in half in preparation for forge welding. First, let's heat this one up close so you can see what the heating process looks like. Next, let's take a look at the full process and how quick it can be from cold material up to forge welding.
For this piece, I'm going to forge weld the end and then draw it out into a short taper. As you can see, the induction heater can be a powerful tool for blacksmiths. With its incredibly short heat times and ability to create custom coils for different needs, it is a versatile machine that can be adapted to many different heating applications. Thanks for watching.